All right, exam 2 review, chapters 4, 5, and 6. The focus tonight is on chapter 5. So, chapter 5 is all about discrete probability distributions. And I'll remind people that discrete means things that are countable or finite in nature. So basically, our variables that we were interested in many times were numbers like 0, 1, 2, 3, out to some finite number n. Excuse me. There was a little bit of difference in there, but not much. A common example would have been something like, the number of baby boys and 10 birds, something of that nature. So at the end of the day, our discrete probability distributions took a look and looked like that. Usually they were presented a couple of different ways, most often in tables. And then we'll have the probabilities here. And there were a couple of requirements for each of the probabilities. The first requirement was that all probabilities had to fall, those values had to fall somewhere between 0 and 1 inclusive. And if we sum or add those probabilities, it has to sum to 1. Those are the basic requirements of our discrete probability distributions. And let me give you an example real quick. I'm going to do something here off to the side where you can't see, using my TI to develop some data very quickly. You figured I would have done this before. All right, so for example, if we've got a coin toss, we're going to toss our coin 4 times. We're going to let x equal the number of heads that we might encounter. And I've got the probabilities here. I'll put them up in just a moment. I need something to refer to because a lot of the stuff, quite honestly, out of chapter 1 that students struggle with fall in the realm or area of language. And so we got a 0.0625. This is also 0.0625. This is 0.25. This is 0.25. And let's see, 375. Yeah, 0.375. The most common outcome. So there's your basic probability, discrete probability distribution. These do sum to 1. All of these are between 0 and 1. And there's a couple of things that I can ask people to do with data like this. I can ask people to find probabilities. So I'm going to put an example or two up here. So we're going to look for the probability of at least 3 heads. And the kind of issue students have with this problem really is in the language. At least 3 heads means 3 or more. That means we're talking about 3 heads or possibly 4 heads in those 4 flips. So the way to answer that question is to add the probabilities together. So 0.25 plus 0.0625, whatever that turns out to be, 0.25 plus 0.0625. I do it on the fly if people weren't watching. 3125. So it's that kind of language. And the kind of language we run into is the at least more than, at most, and less than. So those are the kind of phrases that we run into here. And as I say, students tend to struggle with some of these guys here. At most means up to and including that number. At least means everything up to that number. More than and less than people do much better with than at least, than at most. The other thing that I can ask students to do with these distributions is to find the parameters. I can ask people to find the mean, the standard deviation, and the variance. And this does require our calculator. So let me run through the calculator keystrokes for finding the parameters of a distribution like this. Let me get the, oh, you should have been up and running. This will just take just a moment. Then I'll share my screen and we'll go through the keystrokes. By the way, you see these keystrokes on any number of videos within our Canvas course shell. So keep that in mind. So let's see. Share my screen. There it is. Share. Stat and then edit. You may need to clear lists. Oh, list one actually works quite well. I'm going to keep list 1.0625. 0.25. 0.375. 0.25 on the way back down. 0.0625. And yes, it's well approximated by a normal distribution. You can really see the pattern, by the way, when n gets large here. In any case, I've got the data in there. Then I can come over here to stat, calculate my one variable stats, list one and list two for the list and the frequency list. We'll calculate that. I've got a mean, it says X bar, but it's really mu because of a probability distribution. Notice there's no standard deviation S, but there is a sigma, a sigma, and that sigma is equal to 1. And I've got all the other good stuff as far as the 5-number summary, which is funny because we got 5 numbers. Oh dear, but it all looks good. So let me go ahead and summarize that data. And there we go. And then I'll talk about the one last thing we do with this. So 2.0 heads. By the way, that's about what you would expect if you were flipping fair coins and you had 4 flips. Standard deviation, 1.0 head. Variance, 1.0 square heads. Remember, we square the units as well. Now, there's one last thing that we do with our outcomes. I can ask if we have a significant number of outcomes. This is the other thing that we often do with these tables. And I'll remind people that significant outcomes for X happens when X is less than or equal to 0.05. And sometimes X or more, sometimes X or less. The important value there is the 0.05. So I could ask a question. For heads, is that significant? And the answer is no. And the reason the answer is no is because the 0.0625 is greater than the 0.05 line in the sand, so to speak. So that is why we say no, 4 heads are not a significant number of heads. Now, I got to say one thing about that whole little analysis there about the 0.05. That's a very nice rule of thumb for a significant outcome, but that is not a hard and fast rule, like, say, the Pythagorean theorem. That is a value that we use in this class. Usually, the situation dictates what kind of probability would be regarded as indicating a significant level of success or failure or the like. So the first part of chapter 5 deals with basic discrete probability distributions like that. Then we took a look at the binomial distribution. And interestingly enough, the example I just had up there is an example of a binomial probability distribution. But that binomial distribution had to satisfy several different requirements. There had to be a fixed number of trials. There had to be 2 outcomes. The trials needed to be independent. And the probabilities needed to be constant. They don't change from trial to trial. And clearly, 4 coin flips, heads versus tails, is a nice example of something that falls into that very, very precise description. We had an ugly little formula to actually find probabilities. I won't even review the formula here because we actually use our calculator in a much more sophisticated fashion than just a simple formula. If you really do want to see the formula, you can see it in the Canvas course shell. It is kind of impressive. So our binomial distributions, we do a couple of things here. We find probabilities of exactly X successes in N trials, and then all that at least, at most, etc. And so when we find our probabilities, those are the types that we look at. Now, a little bit about the notation, because that is important when it comes to getting our tools to work appropriately. For our binomial distribution, our notation, X, the number of successes, N, number of trials, little p, probability of success in a, and this is important, single trial. And then finally, we had Q, same thing, but we have the probability of failure in a single trial. By the way, P and Q for success and failure, those are the words that we use. Very rarely is anything truly a success or truly a failure. In my example that I looked at previously, the success was heads. That doesn't mean I've somehow failed if tails come up. That's all. That's a little thing. We do know that Q is equal to 1 minus P. Probability of, honestly, complementary events yet again. So that's the notation that we use. And actually, we need all of it at one point or another as we address the material in 5.2. So let me give you an example of how we handle these problems. My first example, we're going to flip a fair coin 10 times, and we're going to find probabilities. First, exactly 5 heads. All right, so whenever I work with finding the probability of exactly X number of successes when we're working with a binomial distribution, binom PDF or binomial PDF, that's what I use for exactly so many successes. And I will need to provide my calculator with a couple of things. I will need to provide my calculator with N, P, and X. In that order, I believe. I'm going to do this on my calculator. So let me go ahead and share my screen. All right, so distributions, binomial PDF, probability distribution function, number of trials, what did I say, 10. Oh, probability. Sometimes when it comes to probability, I kind of expect students to be able to figure that out on their own. There's only a very small number of cases where I really expect that. Basically, it's flipping coins and having babies. 1 out of 2. The X value that we're interested in here is 5. And there we go. If my calculator doesn't have the stat wizard turned on, I separate these values with my comma located right up above the 7 key. That's the way it looks with the comma stuff. So there's my probability, 0.24609 and change. Probabilities, 3 significant digits. So 1, 2, 3. I take a look at the 4th. So the 6 stays 6, 0.246. Now, let me go ahead and stop the share. And there we go. .246. Now, I'm going to do another one. This one is going to be the probability of less than 5 heads. All right, so this one has a couple of things that we need to keep in mind. First off, what do we mean by less than 5 heads? And this is where students can have issue. So that means 0, 1, 2, 3, or 4. I don't want to include the 5 because it says less than. Less than. Like, no, you can't go as far as 5. Nope. So less than 5, not the 5. Now, that's where I use my binom CDF or binomial CDF. The CDF stands for cumulative distribution function. Now, the notation over here, I am fond of for this particular type of problem. There we go. 0 through 4, including the 0 and the 4. So, here again, I will need N, P, and X. And it's important to realize that when we use the binomial CDF function, it always starts at 0 and it marches up to a particular value. And that has real repercussion for some of our problems, like my next example. Let's get this one done first. So PDF, now let's go back and take a look at the CDF function. There we go. Trials, 10. And probability, 0.5. You can use 1/2 or 0.5 here. I do like fractions because I don't have to round. If I had a fraction of 1/3 and I wanted to use a decimal, I would have to round. The x value in question, we're going all the way up to 4. All right, so 0.3769, 0.377. And again, let me stop my share. So, less than 5 heads. Binomial CDF function, there we go, 0.377. Less than 5 heads. At least 8 heads. This is the one that's tricky. It's another binomial CDF, and I'll point that out in a moment, but we have flipping our coin 10 times, so that means I am interested in x equals 8, 9, and 10. And that is a bit of a problem because I can only count up when I use my cumulative function. I could do exactly 5 heads 1, 2, 3 times, or exactly 8, exactly 9, exactly 10. Note what they are, write it all down, add it all up, or I could realize this is a place for the complement. So I am interested in that guy there. However, I'm going to work with the complement here. So it's binomial CDF again. And to find the probability that x is somewhere between 8 and 10, it's 1 minus the probability that x is somewhere between 0 and 7. So that's the calculation I need to do. Now, to do that calculation, I can actually use this entire expression. So, come with me. There we go. So literally, 1 minus ten trials, 1 out of 2 probability of success on any one trial. The x value in question is 7. And I'll go ahead and I'll paste that in. And I get a 0.05468. So the 8 makes the 6 a 7. So 0.0547. stop my share. So, as I say, my binomial CDF brings me to the correct place, although I've got to do a little bit of work with the complementary event, a bar. But that's an example of how we run through the material with our calculator in 5.2. Now, there is one last thing that we do in 5.2 with this type of material, the parameters. The parameters for a binomial distribution this is one of the very few times we actually need some formulas here. The mean is n times p. The standard deviation, the square root of n times p times q, with q equal to 1 minus p, and the variance n times p times q, remembering to square whatever the heck it is you're counting, be it heads or genders or correct questions or who knows. But those are the parameter formulas, and they are not built into your calculator. So these guys here really truly need to be committed more or less to memory. Yes, I know we have open notes and open books, but quite honestly, there's really not enough time to look at anything or to count on looking something up is what I should say. So let me run through an example with this, and then we'll see where we are. I'm tired of flipping coins. Let's take a look at another question. In fact, we're going to do 2. Yeah, the first, we are going to make random guesses. We have a quiz. Yeah, let's make this one an 8-question quiz, and it is multiple choice. And A, B, C, and D. So if we're going to be making random guesses, and we're going to let X equal the number of, well, correct guesses, I can ask, what is the mean number of correct guesses? What is the standard deviation of correct guesses? What is the variance of correct guesses when we're guessing over 8 questions, each of the questions having 4 possible outcomes? So this is the type of question where I would probably provide the P, not the N, but I would probably provide the P, although maybe not. So let's take a look at that. I said we need N, P, and Q. So N is clearly 8, but I do need P and I do need Q. And remember, that's what happens in a single trial. So if you are going to make a guess on a single question amongst 4 possibilities, and I know my students on occasion guess, only 1 out of 4 of those possibilities will be the right guess. So P, 1 out of 4. Q, 3 out of 4. So once I've got N, P, and Q, I can go ahead and find my mean number of correct guesses. Mu is N times P, or 8 times 1/4, or 2, and I want one more decimal place than x. X is a whole number, so that gives me one decimal place here. I'll get 2.0 correct if I guess under this situation over and over and over again, and look at my long-term trend. My standard deviation, square root of n times p times q, square root of 8 times 1/4 times 1, oh, good Lord, 3/4. What did you come from? This is one where I would probably switch to decimals just because they round so easily, but maybe not. So let me go ahead and run through those keystrokes there. And so literally, second square root, we have 8 times. I'd probably open up my parentheses, but I really don't need to. I can 1 divided by 4 times 3 divided by 4. Order of operations literally guarantees we're going to end up in the right place. And I get a 1.2 and change. That would be 1.2 correct. I'll come back to my screen in a moment. I want to take 8 times 1 divided by 4 times 3 divided by 4 to find the variance. And 1.5. All right, so that was 1.5. Stop my sharing. And there we have it. So, as I said, we need n. Oh, that doesn't look good. We need, as I say, n, p, and q. I usually provide p. N should be easily seen. If I give you p, a student should be able to find q. And then you actually need these little formulas here. And you'll note I've got 1 decimal place for each of these. And we've got the square units right there. There we go. So the 5.2 material focuses really in the areas you just have seen here. So 5.1, distributions. You should be able to use them, and you should be able to find the parameters. And you should be able to do that with your one variable stats. Uh, 5.2, specifically the binomial distribution. And there, we wanted to focus on using binomial CDF and PDF, and the formulas for the mean, the standard deviation, and the variance. And we also want to, when all of this is said and done, be able to identify significant outcomes. And that significant outcomes, you now have a couple of different ways. The probability of whatever that might be needs to be less than or equal to 0.05, or we can also still use the mean plus or minus 2 standard deviations. That'll work for us too. They should be complementary, by the way, for the most part. So there we go. Students, if they've been able to make the calculator work for them, usually do quite well on the material in Chapter 5. It's truly a very calculator-heavy bit of material, and students who have spent the time with their calculator usually do quite well. All right, I'm going to stop the recording because that's the end of my discussion in 5.2.